Hey guys, I am Anthony Scodary. I'm co-founder of Gridspace. Today we're talking about LLM-based spoken dialogue systems. You guys, I hope you guys so far in this class you've done speech synthesis, speech recognition, probably a little bit of like language understanding, language generation. We're gonna be talking about all that stuff in the practical world of kind of how you actually use it in critical settings like hospitals and banks and everything that goes into that. So real quick about me and about Gridspace. Again, my name is Anthony Scodary. I originally went to Stanford. I did physics and then aerospace engineering. After Stanford, I was actually at NASA Jet Propulsion Lab working on spacecraft autonomy for spacecraft signals and systems. So I worked on like the Mars Curiosity rover. I worked on the Juno mission to Jupiter. And I worked on how robots could basically make decisions using instruments entirely on their own. To get better science out of planetary space missions. And a lot of my background originally was on applying signal processing machine learning to robotic autonomy. I eventually became interested in applying deep learning to high dimensional signals, which led me to be kind of an early adopter of deep learning applied to speech. And so what we do at Gridspace, as kind of Andrew alluded, is we work on, this is what I have here, interactive long-form conversational speech and language applications. What this means is we work on things where people are in the loop. We work on long-form conversations, so not like maybe you're talking to a voice assistant where you might dictate a command to an ontology like Siri, but we're looking at long conversations. We work on both speech and language, so we're operating on signals, not just text. And we work on applications, so we're not just like an API. We actually build systems that can be deployed fully into the real world, both for analysis and automation of full speech. So we, like I alluded, work on a lot of the stuff you've been talking about in this class, or probably all of it. This is what we're going to be talking about today. So we're going to talk a little bit about the motivation for task-oriented spoken dialogue systems, the engineering challenges, and then our 4 strategies: control, latency, naturalness, and robustness. A couple case studies from the real world, and then a demo. Great. Motivation. The laser. The laser was first kind of postulated as an application of quantum mechanics in like the 1910s by Einstein. And the first laser was built in the 1960s. This is a Heaney laser. But the first real mass applications of lasers, so like telecommunications, photonics, disk readers, a lot of those applications came 10, 20, even 30 years later after the laser was kind of first prototyped and almost a decade after it was first postulated. A lot of times when you have a breakthrough technology, and the significance of lasers was recognized long before one had really been built, much less applied in some sort of engineering context. And so similarly, when you have any new adopted technology like large language models or automatic speech recognition, you have some sort of like sigmoid-like adoption curve where there's a very long refinement process before you get bulk adoption. One, because the earlier version of the technology is less refined, and because there's a slow adoption, economically, even if there's very high value. Even if, like in the case of lasers, the value is recognized very early. It just takes decades for that stuff to get refined and adopted. And a lot of that process, the last mile problem, how you take something that's a really great paper. So like for instance, in speech recognition, the first end-to-end speech recognition was published over a decade ago, but you only started to see end-to-end speech recognitions become the dominant architecture much later for practical reasons of refinement. And the same goes for task-oriented spoken dialogue systems that further integrate modern large language models into their process. So there's a couple engineering challenges that I want to discuss. So let's break it down. So our goal today is to build a thing that you talk to, or specifically we want a person to solve a complex problem using a machine on the phone. So that's what we do with our virtual agents, Grace. So specifically, what are we trying to do? Well, so we need a machine to do it, the whole point of automation. So we need a dialogue system. You guys know what a dialogue system is. We need it to be on the phone, so it needs to be a spoken dialogue system. We're talking about voice, we're talking about signals. Specifically, if you're on the phone, the most common media you're gonna get is actually 8K audio that go through an ancient codec called G711. So you are solving problems. So you're not just entertaining someone like you might with ChatGPT, you actually have to solve something. So you need a task-oriented spoken dialogue system. And these are complex problems where people might have questions about questions or rely on context for meaning, or have questions where it has to draw from multiple documents to answer the question. So we're going to use large language models and modern other NLU and NLG techniques to be able to solve these complex problems autonomously through the voice channel. This is what that looks like, right? So, we start with like speech recognition, right? Speech to text. It's going through a dialogue system, through speech synthesis, through the internet, through PSTN, which is the phone networks, through the LTE tower networks, to your iPhone, to sound waves, to your cochlea in your ear, your brain, your vocal tract, your sound waves, microphone, all the way back through the phones and internet, all the way finally back to ASR, right? There's this huge loop of things that you have to go through to do a spoken dialogue system. All of these have neural networks, all of these have physical effects, all of these are noisy, all of these have nonlinearity and distortion, all of these are lossy, and then all of them consume latency budget. Everything in this pipeline consumes latency budget. And remember, this is a real-time application. It's, you have to respond in a few seconds at longest. And so unique challenges of spoken dialogue systems, and this is true long before emergence of language models, it's noisy, right? You have background noise, you have reverberation, you have things that are making the audio quality degraded for speech recognition. It's non-grammatical. People can speak in sentence fragments, can answer in just singular words. It's latency constrained. Like we mentioned, you have to respond in a few seconds or ideally less for it to sound natural and to not break turn taking. And then finally, you have to deal with turn taking and interruption issues. People will add corrections or do things that retake the floor. And you need to correctly deal with these kind of complex, pragmatic signals that people use to communicate that go beyond just what words they're using. And those are all the challenges specific to spoken dialogue systems, right? And that's always been the case. Traditional task-oriented dialogue systems, so task-oriented dialogue systems have existed for a long time, actually. I mean, probably over 40 years there have been task-oriented dialogue systems in the text channel. They've traditionally been very burdensome to offer, where very complex formal languages are used to define what they can say. They often have very rigid NLG. Maybe there's a lookup table of what they're allowed to say in certain states in the dialogue state tracker. And they also tend to traditionally have a lot of different language understanding struggles. They couldn't rely on context or things from earlier in the dialogue. And that made them a lot of times too fragile to deal with complex situations. There's a quote I like. So at its core, all engineering comes down to making trade-offs between the perfect and the workable. It's from Katie Hafner, and a book she, I think, read originally about the internet. Engineering is about trade-offs. Practical engineering is about trade-offs, right? So for instance, there's going to be a trade-off between latency and language understanding or language generation, right? We could throw the biggest, slowest language model that's doing, chain of thought reasoning and takes, a second per token, but by the time we generate do our NLG, the person's hung up, right? So, but there's all these engineering trade-offs between building something that meets all of these constraints that we mentioned here in a LLM-based task-oriented spoken dialogue system. And these trade-offs for optimization is kind of what we're going to dive into. All right, so these are the four main themes for optimization. This is what we're going to be talking about mostly today. These are the four things that you need to make better or good enough so that the system can be deployed in the real world. One is control, the ability for the people that are deploying the system, whether it's a hospital or a bank, feel that they are able to represent their business appropriately, are able to make sure that they're compliant, make sure that they're doing what the system is designed to do. Second is latency. So latency, we already talked about, means that it responds quick enough that you can establish a conversational groove, that it feels ideally like a person and reasonably natural. Third is just general naturalness. So, again, spoken dialogue system, there's two big centers in our brain dedicated to consuming and generating speech. It is a very innate thing to generate spoken dialogue, and people are very sensitive to the uncanny valley of this thing feels like fake. And so, the goal isn't necessarily to fool anyone. In general, most of our systems we identify as a dialogue system, but the goal is to make it feel like it is actually speaking natural spoken language and not a tool that you can't really speak openly with or is not useful, because that's going to drive people away from that channel towards other ways of interacting with the business or the customer or the hospital or whatever. And the last is robustness. So how do you, in general, when you're building something for the real world, robustness is everything from just basic engineering principles for stability and scale, all the way up to things very specifically to how you build machine learning systems deployed in the real world that fail gracefully or fail safe. And so that's control, latency, naturalness, and robustness. So starting with control, how do you build a spoken dialogue system where you have leverage over what it does? In the spoken dialogue channel, there's really three things that you do, three tasks that you ever really do. One is question answering. The second is form filling, so filling out a form. And the third is typically routing someone to the right direction. So you can't do anything, get them to the right place. And so these are the three things that we need control over. This is a diagram from Jarofsky and Martin from your book about your traditional dialogue system architecture, right? Where you typically have ASR, and then some sort of spoken language understanding, some sort of DST, where you're tracking some sort of discrete set of states. So like, oh, you're in the, like, I think this is like some sort of airport booking system. So it's like, okay, you're in the book flight state or whatever. Then there's typically a dialogue policy that maps your state onto actions. And then the actions get mapped onto dialogue generation. And then finally that goes to TTS, right? And that's the way that loop is implemented traditionally. By contrast, as you start to incorporate large language models into different aspects of your spoken dialogue system, there's two main ways that language models can help you with a task-oriented dialogue system. And they both involve translating between the world of natural language and the world of some sort of discrete state tracking system. And so in general, like any transformer-based model, whether it's for language or any type of sequence, is very good at some sort of translation. I mean, I think in the original Transformer paper, I mean, machine translation was one of the target use cases because there's a very good one-to-one alignment between the input and output space. And so similarly, if you have a document or you have a what we call a playbook for Grace, where you're going between a set of instructions for what to do and what actually is the like dialogue that gets generated or what form field got filled out, if there's a one-to-one correspondence and you have specialized language models doing those tasks, back and forth between language understanding, language generation, language understanding, language generation, that's the best way to leverage these models, as opposed to necessarily monolithically having it do implicitly all the dialogue state tracking, all the NLU, all the NLG, all at once, because you're then expanding that scope. So if we tile or repeat this strategy between different dedicated control systems that mirror the control systems that are used to manage employees working in a call center environment, which is the environment we're replicating, right? Which is like commercial call systems, right? If you look at that industry, it is a large industry, right? I think there's a fairly high percentage of the economy. I think around 3 million people work in call centers, another 3 million people who just talk on the phone for their job. And there's a lot of calls that we wish we could do if more people could help, which we'll talk about in our case studies. There's three places these people go to learn how to do their job. One is they typically have some sort of web app or some sort of portal. There's scripted systems for scripted call centers. But what it's typically walking them through is what to do in certain situations. It gives them forms. It gives them guidance. We call that a playbook. So we have a system we built called a playbook. It's a form of authoring where it walks you through what to do in certain situations. It's essentially a very simplified website that is a tool exposed to a specialized set of language models. The second is if you want to, in a call center environment, have someone reference a policy or a document, you typically give them a search engine or a knowledge index where they can perform a search, like what to do when the person lost their credit card, and it'll serve them a document and tell them what to do. And so we also provide to Grace, our virtual agent, a knowledge base. And the third is you typically learn through coaching. You have a manager or boss who coaches you. They like literally sit you down. They call them in call centers Y cable sessions because you're splitting the cable in two, and you listen in while they're on the phone. And then you tell them, oh, I would do this differently. I'd fill out this form. You did this wrong. Coaching is a big part of onboarding call center agents, and we have a system called coaching. Sure enough, that does we call it here episodic few shot coaching. Right? Basically, it's a form of information retrieval where you're referencing episodic examples or few shot examples from similar situations in the past. And then you also have the caller themselves, where you're doing the actual NLG, communicating to the person for TTS, and then you're doing the inbound NLU. All of these blue boxes represent two language models, one in and one out. And so again, for the most part, a lot of the dialogue state tracking is being done in a central system that is state-based. It's a simple state-based machine. Some of the DST, though, has been offloaded to external systems. So for instance, if you have a form, and the form is tracking what fields you filled out, you've offloaded the form system or playbooks in our case to doing a little bit of what would traditionally be part of dialogue state tracking. You're offloading into one of your tools. Similarly, if you get some results back from a RAG system, you're tracking, okay, what was your query, what were the results? There are multiple different systems that that leverage some form of information retrieval. One is the knowledge base, and the other is this few shot coaching, where you have past coaching examples that you retrieve based on context. Like I said, each of these blue boxes represents an in and out LLM in most cases. although in theory some of these could be rule-based. In general, NLG output is highly restricted by the inputs by upstream data systems. So all of these systems might say, oh, I would say this is the answer, or I would say this, and then there's one central system that's rectifying the suggestions from these other data systems. And then some of the dialog state tracking also relies on dialog history. So for instance, I call, we talk about this in one of the case studies, someone calls in and says, okay, my car is broken, and then later on we have to generate, I'm sorry, your car is broken, how can I help you with that? We're referencing earlier in the dialog history to generate contextual answers to maybe a later question. And so that also would be traditionally something a little bit handled by dialog state tracking. But we don't just leverage a large context window on a language model for dialog state tracking. We try to make as much of it as possible explicit so we didn't get caught into unpredictable situations or situations where things don't behave the way we want them to. So control, LLMs are acting, like I said, as an interpreter rather than a monolith. What does that mean? That means that we have a specialized set of language models that just does one thing, like generate a search query for a RAG system, or look at a playbook to fill out a form field, right? This reduces the variance, allowing for smaller models, less fine-tuning. You're also restricting interfaces, so you can do more validation and control over these. It also allows the dialog manager itself, the core dialog system, to be more minimalist, to do less. And it's also better for encouraging reliability and truthfulness. And the reason is, if you're stepping a set of models through very restricted processes, you're doing these simple machine learning tasks that have much higher success rates, daisy-chained, rather than in one shot trying to have a language model interpret a big dialogue history and just get everything oh yeah, go ahead.
Do you see any latency impacts by doing a lot of small calls to the models compared to one big call?
Yeah, great question. So the question is, do we see any latency impacts from having multiple smaller models? And the answer is it depends. For the most part, if you look at so if you're just talking specifically about decoding from a language model, the tokens per second, there can be a huge range. A very large language model with unoptimizing autoregressive decoding could be just a very small number of tokens per second, versus like if you have a very optimized small language model, you might be able to generate a massive number of tokens all in parallel. And so it depends. For the most part, running things in series does add some latency drawbacks. So if you are locally running a language model, you're not hitting like a remote API, one language model will probably in most cases be a little faster than like 2 or 3 in a row. But if you actually look at this diagram again, a lot of things are actually happening in parallel. So even though there's lots of little language models, they're not really daisy chained, but rather you have multiple redundant systems that are also all suggesting changes to dialogue state tracking and dialogue suggestions. Does that answer your question?
Yeah, that's really clever to parallelize the system.
Yeah, we'll talk more about parallelization in a bit because there's some changes that we've done in the last year that have leaned into that more. All right, so I want to talk a little bit authoring tools. So authoring, again, if you've seen maybe in Dorowski's book, authoring is the process of giving instructions to a dialogue system for what to do. So it's the human in the loop that is designing the system. For us, we actually use the word onboarding because that's what you call it for humans. But notice that we've built tools for our dialogue system. We've built all our tools specifically just for our dialogue system. And then we've trained all our models to only expect inputs from those tools or to take actions from those tools. So the supervised fine-tuning process or the model training process is built for our tools, and our tools are built for the dialogue system. And so there's a very tight alignment between the tools and the dialogue system because they're designed for each other and they're trained against each other. And all these tools, like I mentioned, take inspiration from traditional tools in the call center industry, but are purpose-built for our dialogue system. And so that's a big part of how we, again, reduce variance and ensure the model is most likely to do the right thing, because you're not just telling it, okay, here's a random website, interpret the HTML, choose an action, which is a hard thing to do well. The next piece of control is knowledge bases and RAG. So in general, we might have a customer that has 30,000 documents that has everything from their policies for, if you can bring pets on an airplane, to what their policies are for adding a third bag, to whether you're able to take all your Percocet that you were prescribed, and they have all these documents that maintain the information that basically guides their entire business. And so the way that you typically do that is if I ask, can I bring my pet on my airplane? And what it'll do is, just like any other RAG system, it'll perform a query against a traditional information retrieval system. and then get back some results from its query, or it might generate multiple queries, and then look for anything that might answer the question. It might be many documents, and you might sometimes have things that are syllogistically related, like if A is true, then B is true, if B is true, then C is true. So it might need to use multiple documents to answer a question. In general, you are trying to do this real time. And so like the query generation model is very small. The information retrieval system is O of 1. Most of your time is spent taking a small number of documents that are as good as possible for that query or set of queries, and then very quickly putting them into a language model and generating a dialog suggestion based on the dialog history. So someone says, can I bring my pet on the plane? Here's the dialog history. Here's the query. Here's the top matching documents. Generate, oh, you can only bring service animals, right? That's a pretty normal way to apply the knowledge base. You know, I have a dot here, role of vector and embedding-based search systems. So in general, there's two ways you can add robustness to, was there a question?
So I was, yeah, I guess I was wondering, like, since you're using LLMs for pre-processing, might be a risk of misinterpreting information.
Mm-hmm.
How do you cope with those risks?
Yeah, so the question is, how do, like, if LLMs are being used for pre-processing, how do you deal with the risks of like hallucinations or invalid inputs or outputs? I mean, we're going to talk a little bit more about hallucination mitigation in a bit, but a lot of what we're doing specifically when it comes to retrieval augmented generation is because we've trained our models specifically to expect stuff that's been indexed in our information retrieval system, and specifically to only answer questions if it sees it in the research results. The model is very likely to say, I don't have information about that, I don't have information about that. A lot of our work the last year, actually, has been trying to make it so that Grace produces more natural responses when she refuses to answer a question that's not in her knowledge base. So, for instance, if you search for pet policy, you got no documents back, the model's been aligned to just say, I don't know. A lot of the work the last year has been trying to better align it to be like, I'm sorry that you have a service animal, I don't know if you can bring the pet, instead of I don't have that information, I don't have that information. Alignment alone isn't enough, though. Splitting things into multiple pieces, of which RAG in all its applications, RAG is an example of stepping a machine through a multi-step process where the steps have lower variance. And if you're aligning those steps to those, to query generation, span generation, language generation, you've reduced the variance of each of those subtasks. That helps as well. But it is possible that the language model will misinterpret the documents or treat them with false authority and generate something wrong. And you have a set of tools to prevent that, but it's not impossible, right? It's going to slip through, especially if you have 30,000 documents. Actually, the biggest source of bad information is just old documents or documents that are in contradiction. And that's something that's we are continuing to work on improving, because if someone has 50,000 documents, or we actually have the ability, we can automatically just sync with maybe your web store of documents, but it could be you've just accumulated all these old documents and you have versions A through G of the same document, and someone says, what's your pet policy? Maybe the pet policy in 2019 was no pets, and then it changed to service animals. The information retrieval system has just gotten back blindly 2 documents, and if you don't tell it look at the date or prefer the date, and either from the information retrieval system or from the language model, it doesn't have ability to rectify conflicting information. It doesn't matter how much you help it with hallucination, you've just given it bad information and it doesn't know what to do.
I have a question. Do you have any scoring technique to see if the response that is related to the question or not?
Yeah, so the question is whether we have a scoring technique to see if it's related to the question. When it comes to just our traditional RAG, normally it's just a relevance score, so how close the document is to the query. When we talk about intent recognition in a bit, we actually do some more scoring using heuristics, because in that case, you oftentimes, if you just try to have a language model do that without any form of RAG, you're limited. But yeah, it's a great question. All right, so just real quick about vector and embedding-based search systems. So in general, I say, can I bring my parrot onto the plane? I have not used the word pet, and I have not used the word service animal. Maybe the policy is you can only bring service animals, right? And so there's a semantic alignment between the question and maybe the document or the policy. There's 2 ways you can solve this, right? One, you can index it with some sort of vector embedding-based search system where there's some semantic fluidity in what gets returned. So parrot is close to pet, and it returns that document. You can also solve it in the reverse, and have when you generate queries, you can generate queries that cover a large number of animals or whatever. You also can solve this at indexing time, where the pet policy is indexed for every possible pet or whatever, so that it matches more queries. But those are the only ways that you can really rectify this. They have trade-offs. In general, the whole point of information retrieval systems is to try to get things to be O of 1. In general, most vector-based search systems have worse performance, especially for very large embedding spaces, very large number of documents. So you have to really take it case by case. For the most part, most of our customers have so few documents. We're more concerned with the real-time NLG that we do with the matching documents than necessarily trying to optimize for semantic matching, because there's normally only a couple documents that are similar. And the query generation system does a very good job of generating all the likely ways that this is indexed. So if someone says, can I bring my parrot? The language model that generates the query is aligned well enough to know, pet policy is probably how this is indexed. And so that's where it's mostly being addressed. And then breadcrumbs and source citations. So we've been doing this for a couple years. In general, if you in the point when the dialogue where you are, we'll show this in a bit, where you're generating dialogue from a document or you're generating it from a coaching example, giving the user a reference to the origin of that information is very important for debugging if it says something wrong. It's like, this is an old document, like we're saying old pet policy. So it's really useful that you have some way to track a breadcrumb to the original source. The last task orientation using playbooks. So again, playbooks is the name that we use for our, the core of our authoring system. This is where forms and intents, and basically it's like a little website where there's forms and links. And again, this limits to the dialogue system to kind of a very limited action space. Like imagine like a, internet for kids. There's like 2 buttons and like maybe 1 form field that it can see at a time. And this is again simplifying the action space for the dialogue policy. So really it's like, okay, I can move on, I can fill out the form field, I can't do anything else. By limiting the number of choices, you don't overload the language model that's being used essentially for the state tracking or for the policy. There's models specialized specifically for slot filling. Slot filling, so for instance, if I want to fill out a date or an address, there's a combination of language models and heuristics, and in some cases, using special data structures. So for instance, if someone gives you a zip code, or let's say an address, validating that it's a valid address, or if someone says I was born on like January 56th in 2025, okay, that's like not a valid date. And so you can do a combination of data stores, heuristics, and obviously specialized language models for language understanding. And then your NLG should also be aligned to assist with navigation and turn taking. So for instance, if the only 2 things you can do is forward to an agent or fill out a questionnaire, and someone says, hey, could I talk to your manager or whatever, you can guide the person and say, well, I can only do this or this, or I can forward you to an agent, does that work? And so guiding someone through the playbook, aligning the model to help with questions about questions or confusions about what the bot is capable of, that's an important part of how these systems are interpreted. All right, and then we talked about coaching. I'm going to show a coaching session in a little bit. Again, this is a form of few-shot training or few-shot training for the model. What this means is if I do a coaching session where I say, what's your pet policy? And the bot says, only service animals. And we're like, that's like a little bit rough. Maybe say, I'm sorry, we love pets, but you can only bring service animals. So you've given it some NLG coaching. Or similarly, if someone gives you their phone number and you want to put dashes in between the area code and the phone number, that would be a form of NLU coaching, right? Or if someone says, hey, can I talk to a manager? And you wanted to click the button forward to an agent, that would be a form of action coaching. And all of these basically go into structured data that gets indexed. And then next time you're in a similar situation, that episodic example goes into the context of the language models for actions or NLU or NLG. And that's a form of few-shot prompting, right? Where you're using past coaching sessions as to say, hey, last time this weird thing happened where someone says they're on a submarine, I was coached to do this. And so just like the knowledge base is a form of RAG, but unlike that where it's just unstructured documents, these are highly structured things that look at the dialogue state to figure out what to retrieve. Okey-doke. This is an example of our debug system. We're going to show this on a live call in a little bit. And we use this to actually dive into how things are queried in parallel and series, NLG, NLU, speech synthesis, ASR. So here's some ASR, here's some TTS, here's some LLM activities. And this allows us to figure out how latency budget is being consumed, where misinformation may be flowed into the system, how everything is phased. When it comes to latency and turn taking, there's two different ways that we identify the floor holder. One is through a traditional signal processing VAD that's fast. The other is through the ASR system that's slow. And this allows us to look at how latency and information flow are working in a specific call and improve that system. All right, so that was control. Next thing is latency. So imagine we call an elderly person on the phone who just got discharged from a hospital maybe 3 hours earlier. This is something we do in one of the case studies we're going to talk about. They've maybe never talked to Alexa or Siri before. They've never talked to ChatGPT. They are confused. They just got out of the hospital. They are hard of hearing. And you have just called them out of the blue, and you need to establish a conversation with them. If you have very high latency, and this goes for anyone, not just that person, and someone says, "Who is this?" and you take too long to respond, they will start to talk again and then reclaim the floor. And then we won't say anything again, and they'll try to talk again and reclaim the floor. And if you have very long latency, you've made your turn taking and interruption handling way more complex. Because now you have to deal with, oh, I've been interrupted 3 times, now I need to respond immediately or barge in. If you have if you have very limited latency, you've restricted your latency, you've made it a lot easier for yourself to have a lot more time to decide when to talk, or to talk as soon as you should be allowed to talk. And so latency is the most important thing if you want to be able to establish a conversational groove, especially on outbound calls. Everything in this whole loop, if you remember, consumes latency budget, so all of them are targets for latency reduction. So in general, a couple things we do with speech recognition. So we do greedy decoding, so we have a very simple decoder. We don't have like a large beam or anything like that. We have an in-domain model that's highly optimized for Grace specifically, or for in the case of analytics, for analytics. And we have specialized VADs, so voice activity detectors, that are not machine learning, that are very simple DSP that allow us to very quickly recognize when we can talk using just essentially silence and a couple other just basic traditional signal processing. And then we solve all the errors that VAD then causes with sophisticated interruption handling. So what that means is, as soon as I stop talking, we have some silence in the line. The VAD will recognize that, okay, we probably can talk. That allows the dialog system to have as much time as possible to generate a response. Because if it gets interrupted, fine, okay, stop. And then wait again for silence, and then start that whole process over again. Oh yeah, go ahead.
Yeah, I have a question on that. A few lectures ago, we explored the concept of having audio LLMs. I mean, VAD is great. There's a lot of techniques, but like the phone signal, 8 kilohertz, very noisy, right?
Yeah.
All sorts of stuff that can happen.
Yep.
And you can break, and then you can have your most sophisticated technique. You have your edge case, right? Mm-hmm. And then there's also the latency that you can have from ASR and all those other components. Mm-hmm. And we explored some sessions about the concept of this audio LLM, like Moshi and these sort of techniques where you have everything like one big model. Mm-hmm. So how do you see that? And have you explored some of those ideas yet? Or do you think that's too brittle for contact centers?
Yeah, so great question. So the question is okay, the phone environment can be a noisy environment. How do you how can you use your multimodal language models versus other noise reduction techniques to deal with that? So in general, you're totally right. So a traditional VAD, especially if the VAD is too simple, is not going to be able to do well in a highly noisy environment. One, we don't rely too much on the signal VAD, but it is built to be reasonably noise robust in that channel. But in general, if you're trying to, so let's just talk about speech recognition, whether it's a language model or a discrete ASR model. There's 2 ways that you can try to make it more noise robust. One is through upstream noise rejection. So maybe you do some noise, some FFT model where you remove the noise, or not a model, you do some sort of signal processing to clean up the data before it goes into ASR. Problem is, if your ASR wasn't trained on data cleaned up that way, you may have actually made it harder for your model. The other way to do it is noise augmentation, right? So your data augmentation, where you train on a large amount of noisy audio, and then the model learns to reject noise. That's what we do. Regardless of whether it's part of a language model or discrete ASR, the way that you do that is the same, which is you make sure that you have lots of noisy labeled data in your training set. Because the speech recognition task, whether it's done by something that also is doing language generation or not, you're going to need to make the model robust, and the way you make the model robust is by exposing it to noise. So TTS, there's a couple things you can do to make it fast. You can pipeline it, meaning that you're generating TTS while you're upstream doing language generation from a language model. You can JIT it, which is a compilation technique. You can bucket by length, so your TTS, you might have TTS generate short utterances together and long utterances together. You can cache TTS output, so if she says okay a lot, you don't need to regenerate that necessarily. Use non-autoregressive models, so we use a model architecture that's most similar to like the WITS paper, WITS 2 paper, if you've seen that. That's a non-autoregressive model, so it's able to generate the whole TTS at a time. And then stalling, so what I've been doing where I'm going and you do that because you're thinking, you're not ready to talk, you can have a dialog system do that as well. The more you want to trim down latency, the more important stalling becomes to indicate pragmatically, hey, I'm thinking. On the LLM side, there's a lot of things you can do to speed up LLMs, many papers on this, I'm sure you guys have seen in 224A through Z. Hardware optimizations, page attention, so you want to have a bigger context window, you can page your attention into memory pages. Flash attention is a highly optimized transformer implementation. Quantization, so you're quantizing things to like float 8s or smaller. Pipelines, you can do continuous batching is one way to do it. Prefix caching, so you're in your 3 different transformer matrices, your key, query, value matrices. You can pre-cache different prefixes. And you can also prefix caching can also be, okay, the first couple words in the context window we've already seen before, so we can just cache all the values in the transformer matrices. You can parallelize NLU requests, so if you need to do a lot of different tasks at the same time, just do them in parallel, which we already showed. Speculative sampling, if you are familiar, speculative sampling, the idea is typically you have a cheap small language model, start to decode, put together a draft, and that can be used to speed up the decoding process for a bigger language model. Data prep, you can, so for instance, you can just tell your model, generate stop tokens faster, don't generate as many tokens. So for instance, like our model that does intent recognition, it just generates one integer, right? So it's really a classifier, right? But you can do that same kind of trick, say, to get models to be more brief. So for instance, your query generation for RAG, generate fewer queries, use shorthand, just the fewer tokens you're generating, the fewer autoregressive steps you need to generate tokens. And then model selection. So specialized smaller LLMs, same with the other models, that makes things faster, trims down latency. All right, so that's latency. It was ASR, TTS, LLM. Any questions on latency? Yep.
Is there any way to reduce latency from speech to LLM? Or I don't think that can be pipeline, can it?
So the question is there any way to reduce the latency from speech to LLM?
Yeah.
Well, I mean, between speech to LLM is speech recognition and then the LLM generations. So what else would you optimize?
I don't know if there's a way to stream it because they're like
okay.
the full utterance.
Oh, I see what you're saying. No, so you're talking about like, can you start to maybe do language model decoding before the person's done speaking? Yeah, the answer is absolutely you can do that. And you can even then start doing TTS on your draft LLM output. The problem is, just one more word can dramatically change your situation. So that's why we have the VAD, which is like, it's kind of the first line of defense of, we think they're done talking, you can begin to take your next steps. It's not as sophisticated as the stop tokens that the speech recognition generates, which is like noise robust, but it allows you to at least have an at-bat to start to generate, response. All right, so that was latency. The third is naturalness. Naturalness is basically, does it seem like a human? Try to make it as much like a human as possible. So we'll start with speech synthesis. And I think in the last year, you started to see this approach get adopted more, but it's something we've been doing for a long time, which is the reason that most TTS models sound, at least historically, like a GPS is because the models, they might be state-of-the-art, giant, transformer-based TTS models, the stuff you're learning in this class. But if the data is of someone maybe on a condenser mic right by their mouth, like they're on NPR reading an audiobook, then they're going to sound like someone reading an audiobook, or they're going to sound like a GPS. And so if you collect your TTS data under situations that reflect the reality that you're trying to emulate, the more closely you reflect that reality, the more effective your model is going to be. So for us, we're trying to emulate the call center environment. So we have our actors wear a headset. They're in an environment that has the acoustics and the transfer function of a real call center. Like we actually literally build a little call center and record them in an environment. It's also all real conversations, not read text, which is harder to do that, because you have to then basically write improv scripts for the actor and a partner to do simulated conversations. And you do in-domain scenarios. So if all they're talking about is ice cream, and then you try to use it for hospital, everything from just words and sounds and maybe sequences of phonemes are not going to be present there. Like for instance, if you want to use it in a medical circumstance, there's a lot of shared morphemes, right? Like if you have pancreatitis, diverticulitis, you start learning all those medical words for your TTS model, it's going to start figuring out intonation and prosody that matters for these medical words. And then idiosyncratic voice actor and direction. So, ideally, not every person is the same. People have different dialects, they have different speech patterns, they have different personalities. Encouraging the actor to emphasize their dialect, emphasize their personality is going to make the model less flat. The process of training TTS tends to be a little bit of a regression to the mean, where it's going to, integrate over a large number of different intonations and prosodies that over the course of their sessions. And so having them exaggerate their intonation, exaggerate their acting will make the model a little bit less flat. But it's a hard thing to do. It's hard to get someone to overact this, especially if that's not how they're used to talking. But ideally, you want to have just a good high quality data set that represents what you're trying to emulate. NLG alignment, there's a lot of talk about how to do NLG alignment. In this context, one, it's, again, call center agents are singular people. They're not every person averaged together. There's a bit of an art to this, but alignment here might be literally the model itself has been fine-tuned to a certain voice, or it might be something as specific as having a backstory or name or job title to the dialog system. You're going to see how we do that. This is a new slide. Reasoning chain of thought aligned models, right? So things like the O3 reasoning model or DeepSeek. These are models that are, chain of thought has existed for a long time, but these are models specifically aligned to do with chain of thought process and to encourage them to do that. There's a lot of fun papers where people have done this in different ways. In general, in the spoken dialogue, these are models, to be specific, that you're encouraging to generate extra tokens, right? Which is the exact opposite of what I said we were trying to do in latency, which is stop early, right? It's the opposite thing. So in general, when you're trying to trade off between latency and accuracy, chain of thought models aligned for reasoning are much more likely to get things right. They're much less likely to hallucinate because they're thinking through what they're saying, which I rarely do when I'm talking, but people are supposed to. And so there's a trade-off. In general, putting a model designed to generate large numbers of thought tokens before it ends up terminating is going to have too big of a latency hit. And so if you want to use a model like this, there's three ways that you can use them in a spoken dialogue system, depending on your application. One is you can help with pre-call planning, which I'm going to show an example of in a minute, meaning that if before you do a call, you're using those models to do some sort of a related task that help you make the call successful. The second is asynchronous call guidance, which you can, so again, with parallelization, this is what I was alluding to earlier. You can have the model, while it's talking, have a offline asynchronous model that's maybe aligned for analysis to review the call as it's unfolding, but at a slower cadence, not synchronous to the call. So out of the critical path for latency, saying like, hey, you know what? Maybe try this different strategy, or this person's like having trouble hearing. Maybe repeat this piece of information so they understand. And the third is post-call follow-up. So let's say that there's some result of the call. So like, for instance, you could have a chain of thought model reanalyze the call and improve your NLU so that the final data is maximally accurate. Those are all things that are not in the spoken dialogue system critical path, where those models can play a really big role. This is an example of, this is an unreleased version of Grace that's specifically able to do large numbers of calls that are actually planned by a dialogue system. So in this case, the dialogue system is running through a very long procedure where it's like looking up businesses to contact on behalf of the user before it calls all of them in parallel or in sequence. In this case, it was a test where Brendan at Gridspace, she had it calling a lot of pizza restaurants and was ordering a pizza for her office as a test. And in this case, all the planning for the call and all the structured information used for the authoring system was all generated by a chain of thought model as part of the call planning process, right? So there's a specific user request to one task, and that's exploded into maybe some sort of author dialogue system that then gets executed. And so we will play a second of this. It's kind of fun.
Thank you for is Dennis speaking. How may I help you today?
Hi, Dennis. Hi, Dennis. This is Grace, a virtual assistant. Can I place a phone order for delivery with you?
No, we do delivery via Postmates,
Yes.
Uber Eats, and Chow Now.
Oops, sorry. Anyway, so yeah, well, I'll play a little bit more here for the people on
Thank you for
CPD.
calling Christian Pizza. And Chow Now.
Thanks for letting me know. Can I place a phone order for pickup? Then,
Yeah, we can place a phone order for pickup.
great. I'd like to place an order for pickup under the name Brennan. The first item is one mummy pie.
So in this case, a chain of thought language model has an advanced simulated different ways the calls will have gone, and thought of in advance. Pickup is okay. I need a credit card. I need expiration date. They might probably need the address. And I tried to think through contingencies as a way to make the eventual critical call more likely to go well. Some other improvements. So back channels. So if Grace is listening to you, make listening sounds. So yeah, I see. Focusing on giving some control over personality and persona, which is part of our dialogue system, which you'll see, and then tracking emotional state. So if someone's berating Grace, she should track. Okay, I should be distressed. I need to show them that I'm reacting to your emotional state with my own change in emotional state. All right, that's thing 3. The last is robustness. Right, you're building any critical software system, like any software system for a bank, any software system for a hospital, any software system for a business is critical. Robustness is important no matter what. It's not specific just to speech or machine learning, but there are things that we care about specifically. All of these things in particular introduce noise, and all these things introduce distortion, information loss. So as I was answering your question earlier, data augmentation is one way you can address this. So your downstream language models, for instance, they should be exposed to ASR errors, whether they're simulated or real. You should also expect that if someone is giving you something like an email or an address or a name over the phone, whether you are, there's a reason people on the phone use the phonetic alphabet, A for apple or A for alpha. It's because it's very ambiguous to give alphanumeric information over the phone or named entities over the phone, because there's many different ways to spell, for instance, a name. And so you have to be robust to that. You also have to close the loop on errors and piecewise corrections. What this means is, hey, I got this as X, is that correct? No, okay, let me try this. So if, for instance, if we collect a phone number and I say, oh no, the area code was 314, not 312, it should be able to do a correction in place. Hallucination management, so I alluded to this earlier. Again, breadcrumbs and chain of thoughts are a way to do this. So even though, like I said, a chain of thought aligned model might be off the table for latency reasons, you can still procedurize the way the dialogue system operates, which is a limited form of chain of thought. It's just not a chain of thought aligned model where it's just free form generating reasoning tokens. There's also other decoding strategies that are less likely to produce hallucinations. We don't do them, but there's a lot of really interesting alternatives to autoregressive generation that are less likely to commit you to a specific hallucination-prone path. And you can also do multi-step generation, right? Which is kind of, I guess, what we are also doing, where you might generate this sub piece of information, then this sub piece of information, and then finally generate your dialogue. I want to talk really briefly, specifically for, I guess, when you're talking over the phone or any sort of conversation, there tends to be inbound and outbound calls, right? So there is the case where you are receiving a call. So for instance, the front desk at a hotel, or there's cases where you're making outbound calls, like for instance, calling patients that just got discharged from the hospital. Inbound calls, from the linguistics perspective, you have user-initiated dialogue and floor holding. That means, I'm the one calling, the human, I'm the one holding the floor. I'm the one that's dictating why the call is happening. It's going to rely more on heavy intent recognition. There's a lot of reasons someone could call in. It's going to rely more on user agenda setting, deciding what the call is going to be about. That means there's way more ways the call could unfold. It's also well grounded from the beginning. Especially, it's very likely the person knows not only they're going to be in a conversation on the phone, but they're prepared to maybe talk to a bot or talk to a machine, because that happens when you call centers, right? And so that earlier scenario, that elderly person discharged from the hospital who gets called out of the blue, it's less of a problem in an inbound case, because the person is more primed to know that, hey, I want to talk about X, and I'm going to talk to a machine about it. There's also a larger implementation risk. The reason is, if there's mitigations, but for the most part, if you have a bank and your bank has one 1-800 number, and you're saying replace your whole front of your call center with this bot, that's a scary thing to do. It's hard to do incrementally. You can have your phone system sometimes route to the bot, test it, but it's more complex to roll these systems out. Outbound are the opposite. So this is system-initiated dialogue and floor holding. So pragmatically, so in like linguistics, the way that we communicate at the higher level is framed by the system. So I, as the machine, am saying we're going to go through this form. I'm going to ask you, are you doing this or this? And so it's harder to establish common ground. It's harder to get into a conversation flow, because the person needs to get into the rhythm of talking to the machine, needs to know that they are talking to a machine, but there's also lower implementation risk, because so we probably do 80% of our calls are outbound. Imagine that your company has an initiative where we want to start to rely more on language model-based spoken dialogue systems to be part of our call center solutions. You can toe dip into it and be like, let's do 10 calls and see how they go. Let's do 1 call and see how they go. And so you can test, with very small sample sizes, incrementally roll it out. It's not uncommon to test 1 use case, then roll out 5, then roll out 10. And so there's trade-offs. There's a lot of people that are comfortable, their first toe dip into the world of having language models talk on their phones. This is probably more comfortable, but you're calling people who might be hard to just get them talking to the bot in the first place. So there's trade-offs. They're both hard. Finally, this is our trust and safety rules of the road. We give this to all our customers. I'm not going to go through all of it, but the slides are on the website. But basically, there's a lot of different things you can do to improve trust, safety, reliability in your systems. So again, in conclusion about these 4 solutions, these 4 problems, right? Robustness, latency, naturalness. We've architected the system so that language models play a central role, but they're not the whole dialogue system. We're trying to keep things on track. We're trying to keep things in a flow where there's error correction, where models are doing as little as possible with low variance as possible. So a few case studies. I'm going to talk about 3 of our customers. Some of them are anonymized, some of them aren't. The first one is Incept. This is not anonymized. Incept does a large percentage of the nation's blood drives, so for blood donation. Blood donation is local and it's an institution specific. I've talked to Stanford's blood drive folks. Stanford Hospital is an investor in Gridspace. They have no trouble getting blood because they have a bunch of, you guys, just donating their blood, just walking around. And so they don't need to do blood drives. They literally, there's students everywhere that just have tons of blood. But if you're in like rural Ohio, where they also need lots of blood, they might not have a bunch of just students donating blood who are altruistically doing this. And so they actually have to call people and get them, hey, you donated blood 2 years ago, do you want to donate blood again? This is a critical thing. Blood doesn't sit around forever. You have to continuously do this. And it's happening around the world, right? And so Incept is a company that does a large percentage of the nation's blood drives. The more calls they do, the more blood they get, the more lives they save, right? And so they have rolled out Grace across all of the blood banks that they represent, which is a large number of them. And they've been able to substantially increase blood donations across the country using this, right? This is a case where, and you see this all the time with outbound calls, the purpose of automation isn't just, let's replace the people that are doing the calls to now. It's like we can afford to do 200 calls now, but now we can do 2,000 calls, or we can do 2 million calls, whatever they need to do. This is huge for changing the economics of blood donation in their case. And they recently, at the National Blood Donation Conference, did a talk that we posted, or we did a talk with them about this if you want to learn more about it. But these were outbound calls, calling people who have an established relationship with their blood donation system, but maybe they haven't talked to them in 2 years. So they're not easy calls. They are simple calls. So you're trying to encourage someone to donate blood, schedule donation, stuff like that. This is a slide from Incept about what they did. They called it Betty Blood. We also, recently had a large application with a national car dealership, and I'll anonymize them in this case. These are inbound. This is people calling. They go 100 different reasons, hundreds of reasons they could call. They bought a car. The car's broken. They wanted to ask a question about the warranty. They want to buy a car. They want to know about locations. There's all these different reasons people can call. So it's inbound. People expect to talk to a machine. They had a worse machine before that wasn't, a dialog system, but it was an IVR, the kind of plastic old style systems. And they have hundreds of possible intents. That's hard because you need to be able to deal with all these different intents. And it's also really important to do contextualized NLG, where someone says, okay, my car isn't working. There's a lot of reasons they might be calling. Maybe they want to repair the car. Maybe they have a warranty question. You want to at least be able to say, sorry, your car isn't working. How can I help you? Or trying to, what are you calling about? The third use case, this is one of our largest customers, is the largest hospital system in Texas. Every single patient who gets discharged, pre-visit, they get called by this bot. So there's a large form filling task. You're asking, have you picked up your medications? Do you have signs of infection? Did you follow your discharge instructions? These were previously calls that they could not service, right? They didn't have enough PAs or nurses or nurse practitioners to do these calls. And so they were impossible to do the volume of the calls that they want to do. They've aspired for decades to do these calls. Significant improvements to outcomes. For instance, classes of cardiac or diabetes patients that are supposed to get regular calls that never were, to remind them to do specific regular visits, they were finally able to do these calls, right? So this is a really big deal to be able to do these. All right, so the last thing I have is I'm going to quickly show you the demo, and then we'll do last questions. So, mind if I save it till after the demo? All right, sorry, I promise I'll remember. All right, so this is an example of our playbook, right? The playbook is essentially a tree, like a website, where we can give it scripts or dialogue suggestions and forms. These are intents, and this is like a form that's going to fill out. So I'm going to call into like this 224S bot. The bot also has a personality, it has a name, it has an organization. It's part of the 224S family. It also has a knowledge base attached, which is information from the 224S website. And so I'm going to call in.
You've reached the Stanford Spoken Language Processing Hotline. My name is Grace. How can I help you today?
Hey, Grace. I wanted to talk to you about my final project.
Okay. I'd be happy to assist you with your final project. What specific aspects of your project would you like to discuss? What topic are you considering for your final project?
Yeah, so I'm considering building a multimodal language model that also can smell.
Got it. That sounds like an innovative and ambitious project. Could you please explain the goal of your project?
Yeah, the goal is to integrate a language model with a mass spectrometer.
Okay. That's a fascinating project idea. Integrating a language model with a mass spectrometer could have a wide range of applications. However, it's important to consider the challenges that may arise, such as the need for a large and diverse data set to train the model. Nonetheless, I'm confident that you can overcome these challenges and create a successful project. Great, thanks for your submission. You'll hear back with approval from the class staff soon.
All right, so remember this is like a coaching session, right? This is a chance for us to train the model. So if I wanted to correct, I'm going to want this to be more brief, maybe like multimodal smell model. I can correct that, and you can see now it's studying it. It's putting this into its like few-shot prompting. Or maybe we can say like, that project sounds stupid. And that'll save it as well, and that'll go into its examples and help align the model to what we wanted to do in the future. You can see all the systems that I leveraged here, the knowledge base that it's retrieving information from, the playbook that kind of guides the general flow. Here, some of the times it's improvising, and sometimes it's using the script. It's also picking intents from a discrete set. It's filling out forms, and we can add additional forms here, just like a Google form, right? And just pick whatever type of entity we want to extract, and all of those have different NLU behaviors. Okie doke. So that is that it? Oh yeah, if you want to join us, there's like a zillion people from 224S who've worked at Gridspace and work at Gridspace. A lot of people in this room, I think, will be at Gridspace this summer as interns. Here's our references. Now, I know you had a question, so you're first up, but we will move 2 questions, so go ahead.
Could you walk a little bit through like a flow when the customer reach you and ask for a service, like how do you adjust the models?
So you're asking what's the flow when someone contacts our bot?
Like you had 3 different cases for hospital, for like dealer, and for like each case it's unique. How do you adjust model for each case?
Right. So what we don't do is train a special model for every customer. Every customer uses the same models. There's exceptions, like I know Maya, you're like, we have customers that do have their own special models, but they're big. They tend to be like Fortune 100s that have been working with us for a while. The biggest benefit tends to be on speech recognition. So for instance, we have a customer that's a very large hedge fund. They've been using Gridspace for a very long time. They look at earnings calls. Those are really, really out of domain for us. And so we have a model just like for that industry, right? But for the most part, most of what changes is the inputs from the data systems. Different playbooks, which is just data. The knowledge-based data, which is documents. And then these few-shot coaching examples, which again are just all data. So it's just the data changes, the engine and the models mostly stay the same.
Two questions. Okay. So first regarding TTS, you said you're using a model based on fits, right? And then how do you handle streaming in order to keep the prosody and the intonation if it's not auto-aggressive model, you're not generating tokens in real time. Mm-hmm. So how do you handle after you have the NLG preparing the response and then generating the TTS in a streaming fashion, so you don't break the sentences in order to break the prosody?
Sure.
And the second one is regarding the dialogue. Those intents, is that something that you need to generate manually, or something that you have a model generating as well, given the script of the conversation?
Great questions. Okay, the first question is, we use a non-autoregressive model for TTS. If you've read the Witz papers or if you've seen other non-autoregressive models, it's generating all the audio together. Or actually what it's doing is there's a derimeter generating predictions of durations, and then from the derimeter plus the input, it's generating the audio. This is opposed to like something like Tacotron, where you might autoregressively generate the spectrogram, and then you might have a vocoder generate samples, right? That's autoregressive because it's like spectrogram, or MFCC. So the question was, okay, how do you not have, if you're doing it all at once, how do you not have like breaks in prosody? And the answer is the Witz model should only be generating ideally one full block of NLG at a time. Now, I think you're smart enough to know that it can't generate infinite sized outputs.
And you have to diminish the latency as well, right? That's the entire goal, right?
Yeah, so also you're worried about latency. But the thing is, the generation time is pretty much independent of how long it is, because it's not autoregressive. But yeah, it can't generate infinite length audio. It can have a really long a period it can generate. But if you are in a situation where it needs to generate 17 paragraphs of audio, which is rare, what it'll do is split it at sentence boundaries. But it's a good question. So I'm not going to name names, but there's a company that recently started building a spoken dialogue system that I was listening to the other day, and they have really, really tight latency. And the way they do it, really aggressive endpointer, but they also are streaming their TTS, I believe. But because they are using an autoregressive model, you see a second in, the prosody just has a discontinuity. It sounds awful. And it's exactly what you're worried about. Second question, I believe, was do we generate in advance all the intents, or are they all programmed? That's what you're asking? So control, like I mentioned. So to set the context, everyone at Stanford very excited about, any of you know any CS majors that aren't AI track or whatever? If everyone here very excited about language models. Outside of this world, in the world of hospitals, there's a lot of people who are unaware or scared or have used ChatGPT once and don't understand what it is, or they think that it's sentient. And so there's the world out there. There's a lot more uncertainty, a lot more liability, absolutely, compliance restrictions. And so 19 out of 20 of our pilots, they are not saying, can you make it say more random stuff? They're saying, can I make it so when they say they don't smoke, we say, good job, don't smoke. They want more and more and more control. They don't want it to be doing tons of NLG. This might be kind of shocking. You might think that everyone just wants to talk to ChatGPT. They really want just a machine, a iron machine that pumps them through a form. And you can't really blame them, because these are not necessarily, we're not trying to build people's friends. We're trying to build a thing that is doing a political poll, or a thing that is making sure that you didn't take all your medications today. It's not intended to necessarily be that fun. or even that conversational. And so as a result, for instance, what intents are supported, we require them to be user generated. You know, you're actually, it's a good question because it's hard to think of in advance all the intents that someone could think of. It's very easy to have a language model generate all the intents and it'll do it well.
Can I make a point?
Yeah, go ahead.
The problem in the SaaS space is like
Yep.
if you don't have anyone with savvy enough in order to build these dialog trees, right? So
Yep.
if you are selling on a SaaS fashion, like okay, it's your credit card, your IVR,
Yeah.
that's it. How do you handle these? Because it's very intricate, right?
Yeah.
So how you handle that in a way so you have your customer in this case who's created that IVR, right?
Yeah.
In a way that's going to be natural.
No, that's absolutely right. Like, yeah, like, you know, in general, when you have people using software, they, you know, it's hard for them, that you're giving them more work to do. It's a worse software experience, right? Think about it like building a website. Like, where, you know, you typically, it's not uncommon for our customers to have their digital channel, like their apps, their websites, where you can fill out a form, and then this dialogue system, and they can do either, right? And you want them to be as integrated or similar as possible. When you are building a website, the main thing you're trying to optimize for isn't necessarily, oh, let's have ChatGPT generate this website, although I guess that maybe it's changing. Is this an optimal website? Is this confusing to users? Is this like, am I following the rules? And so there's a lot of effort and time that goes into designing maybe your web application form for like depression screening. They're not trying to like speed run it by having, you know, LLM generate it. A lot of care and thought and meetings and whatever is going into rolling out that web app. The dialog system is very similar, right? There's, for every, you know, question in this dialog system, there might be a lot of thought about what they want this model to look like or what they want it to do. And so the 2 seconds of cost savings of it, you know, a language model generating all the intents, one, it can probably do a pretty good job. Two, that's a good thing to do in a lot of cases. But most of our users, they are going at a slow enough pace and they're cautious enough that hasn't been their bottleneck. 5-10 years from now, models get better, people get more comfortable, that could change. But like, you know, you see other authoring systems like Dialogflow, where the main way they tried to jam LLMs in was have it just generate lots of intents. That's exactly where people definitely don't want that automation. What they want it to do is be smart about recognizing the intents. So.
Here, how about we'll break, and then if there's more questions, please just come up to the front. But thank you, Anthony.
I think, guys.